Okay, so picking up where we left off, this is a review of the last slide from the previous um, video on this topic. So to review, we have a volume embedded in pressure surfaces, and what we're doing is studying the continuity equation in pressure coordinates, which is written here on the top here. And yeah, so the concept from last time was that is indicated here by the equation. If we have divergence along a pressure surface, the horizontally, vertically d omega dp must be the opposite sign. So in the case of this example, du dx is negative, which means convergence, and that's going to cause diverging vertical motion on the top and bottom of the box here, indicated by d omega dp must therefore be positive if du dx is negative. So remember, omega is the pressure velocity. So in the top here, sinking motion means omega is positive because pressure is rising following the motion, and that positive omega increases as you go further along pressure, going in positive pressure going down the atmosphere here. So as you go along positive pressure, omega is getting bigger and bigger, and therefore d omega dp is positive to offset the du dx being negative. So the point made last time also is that the continuity equation in pressure coordinates gives you a vertical velocity distribution, but doesn't give you the actual size of the velocity. So that's what we're going to go into now. Okay, so moving forward, what we have here is a stack of pressure surfaces. So going up the atmosphere, we have different pressure surfaces getting smaller and smaller in pressure as you go higher and higher up because pressure decreases with height. So pressure increases downwards, Z increases upwards. This might be the troposphere, so let's take the first level as the surface pressure, and up here at the top, let's say we're around 200 millibars around the tropopause. Okay? Furthermore, let's assume we have a velocity profile, horizontal velocity profile as such. And so if you look closely here, what you can see, what I've intended to draw, is that as you go higher and higher up in the atmosphere, the velocity pattern switches to be one of convergence in the lower troposphere to one of divergence in the upper troposphere. So the arrows leaving the column are bigger than the arrows entering the column up in the top, and at the bottom, the arrows entering the column are bigger than the arrows leaving the column. So you have convergence at the bottom, divergence at the top. And this is very common in large-scale meteorology, that you have this kind of offsetting effect of the divergence pattern as you go through the troposphere. And we'll talk more about that as we go along. But this situation here kind of indicates what the vertical velocity profile might look like as you go up incrementally through these little stacks of pressure. And that's what we're going to show right now. Okay, so this is just an illustration of what we just talked about. In the lower part of the troposphere, we have convergence. In the upper part of the troposphere, we have divergence. This is just the example we're using right now. That implies there's a level right in the middle where the divergence is zero. And that's kind of indicated here in the where I'm indicating with the pointer. The arrows entering are the same size as the arrows leaving, and that's kind of the crossover point from convergence to divergence in the horizontal velocity. It's called the steering level also often in terminology used in meteorology, but you know, keep an eye out for that terminology. For now, just realize that this is a level where divergence is zero. Okay, so to add to that diagram, we now indicate below what we're calling the lower boundary condition on vertical velocity. This is kind of what is needed to set the level of vertical velocity. I remember before we were making a point about the continuity equation giving you a distribution but not a value. Well, to get the value, we need to kind of have a starting off point. So at the surface, vertical velocity 0 because you don't have flow through the surface. So we're going to set W not equal to 0 based on our relationship above. That's going to imply that omega naught is also 0 at the surface. Okay, so that's what we're going to use as our starting off point. And let's see what the implications of that are when we grind through the columns, what the vertical velocity profile will look like. So putting this all together, we now can infer what a profile of vertical velocity would be consistent with the flow pattern horizontally. So if the vertical velocity is 0 at the surface and you have convergence in the lowest pressure layer, that means you must have divergence in vertical velocity, and you can see that we can kind of indicate a vertical velocity arrow that would be consistent with the horizontal convergence pattern. Let's just say this is. Okay, so then now subsequently, if we go to the layer above and we still have convergence in the horizontal velocity, we in turn have divergence in the vertical velocity, and that kind of adds at the layer of pressure above the adjacent lower pressure level, we have a higher vertical velocity because we must have increasing values of vertical velocity with height to offset the convergence horizontally. And then you can kind of imagine as you just grind upward through the pressure levels that as long as we maintain consistency with the horizontal divergence pattern in the vertical velocity profile, everything should just take care of itself. The interesting thing is because we're switching from convergence in the lower troposphere to divergence in the upper troposphere, the vertical velocity profile switches from being increasing as you go upwards in the troposphere from the lower troposphere to the middle, to a decrease in vertical velocity as you go higher up in the atmosphere, and you go from the middle of the troposphere to the upper part of the troposphere. So there's this kind of bow shape in the vertical velocity profile that's very typical of large-scale systems. This maximum of vertical velocity at the middle of the troposphere is actually quite common. This is where you typically have highest vertical velocities. They're either there or sometimes a little bit lower down, maybe at 700 millibars. Somewhere between 700 and 500 millibars is a typical place where vertical velocities tend to be a maximum. Again, I mean, another point to make here is although the arrows kind of indicate that the vertical velocity is the same size as the horizontal velocities, note that these are not at all drawn to scale. Typically, horizontal velocities in the troposphere, mid-latitude troposphere, are on the order of 10 to 100 meters per second, whereas vertical velocities are on the orders of centimeters per second. So it's like 100 times smaller. But there's no way we'd be able to illustrate anything if I drew the arrows to scale. So hence we exaggerate the actual size of the vertical velocity in illustration so that we can study and make decent illustrations. But bear in mind that vertical velocities are quite small, and they are of a size that matches the size of divergence in the atmosphere, not the size of the vertical velocity. I mean, it's not the size of the horizontal velocity itself, but more the divergence of the horizontal velocity. Anyway, back to the point here, this bow shape and vertical velocity. So what we'll do in our exercises going forward is you'll do some calculations of actual values so you can get comfortable with this procedure of starting from a given vertical velocity at the surface, or maybe somewhere else, maybe at the top, depending on how I specify the problem, and using the continuity equation in pressure coordinates to grind through what the vertical velocity profile must be. And you can translate between omega and W by just using the relationship omega equals minus rho GW. You'll have to calculate densities using the gas law, for example, to do that, but that's not a problem. We've done that before. Okay, so here is a summary slide of the end result of what we did. So this is a very typical type of diagram that you see in to kind of summarize the points we are making in this idea of the continuity equation, divergence, and vertical velocity offsetting that. So on the left here are two examples of a profile of divergence in the velocity, horizontal velocity on a pressure surface. The blue being one where you have convergence at the surface, negative divergence, and divergence aloft. And somewhere at the top here, the troposphere, everything goes to zero, let's just say. And then the dashed red one is an example where you have divergence near the surface and convergence aloft. So, and then that's similar to the examples that we used in the previous slide. And you can see that for the situation that we had in the previous slide, that's more the blue line, where you have convergence below and divergence aloft. Omega turns out to be negative. Oh shit. Omega turns out to be negative, meaning upward vertical velocity. With that peak right at the center. This is what they call the level of non-divergence. I called that the steering level before. And the opposite pattern shows up if you have the opposite convergence-divergence pattern. It's just the same kind of pattern, except that instead of having rising motion, or omega equals a negative here, you have sinking motion, or omega is positive. So you can just flip the profile and you get the flipped vertical velocity profile. For well-developed cyclones and anticyclones in mid-latitudes, the level of divergence is typically between 500 and 700 hectopascals, or 500 and 700 millibars. That's the point we made. Maximum magnitude of vertical motion, upward or downward, occurs at the level of non-divergence. Vertical profiles of divergence and vertical motion. Okay? Summary slide of everything we just talked about. This is called Dyne's compensation as another term for this idea. So the compensation part being divergence is being compensated by convergence in the vertical velocity profile. So horizontal divergence compensated by vertical convergence and vice versa. So that's kind of a mass continuity idea, meaning that in effect, spreading out of pressure surfaces is in effect accounting for the mass buildup as you got horizontal convergence and divergence into columns of air. So that's how you might make the analogy between the height coordinate version of the continuity equation to the pressure coordinate version of the continuity equation. Okay, so let's look at another consequence of the continuity equation in pressure coordinates. This is just called the surface pressure tendency equation. So not only does vertical velocity develop as a result of convergence and divergence in the horizontal velocity profile, but surface pressure can build up or decrease as mass is fluxed out of or into the column as a result of the divergence in the horizontal wind. So to illustrate this is Holton section 3.6. And what I've done is cut out the first page of this, and you can see here the pressure tendency equation, which is the vertical integration of horizontal divergence in the pressure coordinates. If you integrate that, the total amount of divergence vertically, you get the total mass leaving the column, or entering the column, which then equates to surface pressure either building up or decreasing as a result of mass piling up or being removed from the column. That's the idea behind it. To see the math behind this, remember omega is minus rho GW approximately if other terms are dropped, but in general, we could look more closely at this now and break up the definition of omega into its partial and advectant terms. At the surface, wind velocity is 0. So the actual equation for omega is the local change in surface pressure with time is omega. If that's assumed to be 0, then omega is 0 at the surface, and that's kind of what we did originally. But now let's generalize this to allow for surface pressure to build up with time, and that's what we'll do now. So omega at the surface is the local change in surface pressure with time. That is going to be when we vertically integrate the horizontal divergence of the wind vertically. We can see how the mass can pile up or build or be removed. Now let's look at that more closely now. Okay, so this is the diagram. So this is a very similar diagram to what we had before. And what we're indicating here is that we got higher divergence. We got divergence aloft and convergence near the surface, just like we've always talked about. Let's assume that there's slightly higher amounts of divergence aloft than convergence below. And I've kind of indicated that with the arrows. When you look at the next slide and flip back and forth, perhaps you can maybe visualize that. But you just kind of take it as an assumption here. That's the conditions of the problem. So if we have higher divergence aloft than convergence below, we're going to be pulling more mass out of the column from flow above than pushing mass into the column from flow below. Remember, if you have convergence, more mass is going in than leaving, and if you have divergence, more mass is leaving than coming in. So if there's more divergence aloft than convergence below, you're going to have a net mass flux out of the column. And remember, surface pressures in a hydrostatic atmosphere is simply the weight of the atmosphere above the surface. So if you're pulling mass out of the column, there's going to be less weight of air above the surface, and surface pressure is going to decrease. And that's exactly what the surface pressure tendency equation is indicating if you were to look at this and study it. So if you vertically integrate the divergence, meaning if you add up all the divergence in all these layers, and so you'll have negative divergence below and positive divergence above, the residual of that, when you add up everything in the column vertically integrated, is going to be the total mass change in the column, which is by definition in a hydrostatic atmosphere the change in surface pressure, because that's just the weight of the atmosphere above. So divergence so in this situation, divergence in upper troposphere is greater than the convergence in the lower troposphere. Surface pressure therefore drops with time. The rate of mass removal from the column aloft exceeds the rate of mass addition near the surface. So this is the points we just made. Likewise, we got the opposite situation here. We got lower divergence aloft and higher convergence near the surface. More mass is piling into the column from below than is being removed from the column above. Therefore, surface pressure will increase with time. And that's exactly the chain of bullets right here that indicates that. So again, all we've done in this video lecture is introduce the equations, introduce the definition of omega, and talked a lot about divergence and convergence in the horizontal wind, and illustrated the consequences of it qualitatively by drawing plots here of what the vertical profile of velocity would be and what the surface pressure increase or decrease would be, just in terms of sign, if you have a certain convergence and divergence pattern in the troposphere. We have not done any actual calculations of numbers. That will be left for an exercise that I'll set up for you guys so you can actually get comfortable with the procedure of tying the continuity equation to vertical velocity to surface pressure tendency. So thank you for watching. Enjoy.